let's take a look at project number 5. Now, right up here in red, if it's in red, please read it. Read it, read it, read it. Okay. The flip machines do not have GPU cards in them. This is a GPU project. Okay. You can compile on flip, but you can't run there. And this will apply to project 6 as well. So do not try and run on flip. And even though it says it here in red and big letters, I know about 10% of the class will start posting on ed discussions. I'm running it on flip and it doesn't work. What's wrong? Okay, flip does not have GPU cards in it. Rabbit does. And so if you SSH to rabbit.engr.oregonstate.edu, that's a machine that looks like flip, but was set up just for this class. So that's a pretty good place to do your development and your debugging. The DGX is our mini supercomputer with 96 NVIDIA cards in it. Well, you're not going to run on 96, you're going to run on one, but these are much faster cards. And so I encourage you to take your final numbers on the DGX machine. Do your debugging on Rabbit, though. It's a lot friendlier. And if you have to, you can take your final numbers on Rabbit, although you'll be competing against other people, so you'll have those little blips in your curves probably. Also, CUDA is an NVIDIA only product. It will not run on Intel GPUs or AMD GPUs. If you've got an Intel or an NVIDIA GPU in your own system, sure, go ahead and run it there. That'll work fine. If you don't, run it on one of our systems. All right. If you look at the first part of this, this looks remarkably similar to Project 1. Well, because it is Project 1. It's Project 1 with some different numbers, but it's exactly Project 1. And so if you want to take your numbers from Project 1 and plug them into your CUDA code and see if you get the same probability, well, that's not a bad way to do some of the debugging. But don't expect to get the same probability when you use the correct numbers. Okay, run this for at least 5 block sizes, and you can do more if you want. Yeah, I went crazy and went up to 256 in mine, and I went up to 4 meg in mine. But basically, you're just trying to get enough points for the graph. Notice there's not a numt in here. We are not doing threading, we're doing GPU. And so we want block sizes, threads per block. That's these smallish numbers. And we want num trials, and that's the same as Project 1. So yeah, try something small, something big. Okay, make sure your num trials is a multiple of 1024. I just want the blocks to come out evenly. You can program around it, but I'd rather that be one thing you don't have to worry about. We're going to use CUDA timing. It's in the notes. It's also in the sample code. And you're going to produce a rectangular table and 2 graphs, just like before, but it's going to be performance versus num trials, and the colored curves are going to be block size, and performance versus block size, and the colored curves will be num trials. This should be fairly familiar. Process is the same. Okay. Yeah, choosing the runs with the most num trials. What do you think the actual probability is? It's a different number than you got in Project 1. Skeleton code is right here. Left click if you want to see it. Right click if you want to download it. Yep, there is a skeleton of CUDA code. Here is the radius of the hole the ball is supposed to fall through. We have labeled it as device because this is a quantity that needs to be in the GPU. The GPU needs to know about this. The CPU needs to know about these other things. These are the arrays. You had them before. They had different names. Anything with GPUs, I begin the host, the CPU version of an array with an H, and I begin the device, GPU, version of that same array with a D, just to try and keep them straight. Okay, Here we go. Here is the Monte Carlo code. It's labeled global because this is going to automatically be sent over to the GPU. What are these goofy define in and out, define them to nothing? I do that sometimes. That is, we're passing in all this information. This way I can label it with, and because it's defined to nothing, there's no harm done. And then this is out. So we're going to pass these arrays in, and we are going to pass out the number of successes. Now, before in the CPU version, you were counting up. You were doing a reduction, counting up the number of successes. We can't really do that here because your threads for this kernel are all over the GPU. But what we can do is set up an array in GPU memory, and every thread is going to either set its element of that array to a 0 or a 1. And then at the end, we'll add them up in the CPU. Okay, so that's the idea. We talked about this in the CUDA notes. This is the GID, the global identifier. It basically says for this one instance of running this kernel, which element am I? So this will be a number between 0 and num trials minus 1. We're going to set its success to 1. And down here, if this succeeds, we're going to set it to 0 here. And down here, we'll set it to 1. Yep, we are reading these out of arrays just like before, or I'm sorry, reading these out of arrays like before. We're computing these just like before. Because this function is labeled underbar global, underbar, it will automatically be sent to live over in the GPU. Okay, here we are setting up the host version of the arrays. Here we are mallocing, that is in the GPU, we are creating these arrays. Okay, they are D arrays, so they're device arrays. And this is how big they need to be, like num trials. And this is in bytes. So size of float will be 4 bytes per float. Okay, and we're mallocing this one, which is num trials times integers. We're doing the host memory copy host memory to the device. Yep, go look up in the notes and see how to do that. I've left all the CUDA isms here alone, except for the arguments. So here is the call of that kernel function. Here we've set up the number of blocks and the number of threads per block. And well, you get to fill in the arguments. Here's the timing. CUDA is capable of doing its own timing, which I've got to believe is better than what OpenMP can do. Here we're copying the successes array back, and here we're adding up the number of successes, and from that computing the probability and printing it out. Okay, so the logic is basically the same. We are just isolating the innards of the code, and we are going to run that over in the GPU, and we're going to run lots and lots of instances of it. Okay, you notice in your CPU code in Project 1, you had a for loop. Here we don't. Well, this is really the implied for loop. Well, really from here on down. This is the implied for loop. It makes a for loop by sort of broadcasting this all over the GPU. So yes, it's missing a for loop, but we don't care. This is how it works. So right click on that. You can get that skeleton code. Notice it's .cu, it's not .cpp. You're also going to need these .h files. Just right click on them and download them. Okay, on Rabbit seems to run best with CUDA version 10. It's a little bit old. It's this graphics card. It's a little bit older. Okay. I'm still experimenting with what version works best on the DGX, but I'll show you later in this video. Here's the bash script. Okay, here we go for trials, here we go for block size, and here we go for running it. So, I want to point out again, num successes plus plus is not what you do. You're filling a global array with either a 0 or a 1 for each test and adding them up later. All right, if you're on Visual Studio on your own system, yes, you can run this. Just get this zip file and it should be all set up with this version of the sample code in that zip file, or when that you unzip it and you get a folder, it's called kernel, kernel.cu, because that's what Visual Studio wants to call it when you set up a CUDA exercise. But it's there. And yes, it still has the question marks and all of that. If you're on your own system, and this is the first time you've tried to run anything with CUDA, you're going to need the runtime. Get it here. Just click here. It's already been set up with x86, CUDA version 11, and an exe should just run out of the box. Yeah, okay, I know that never works. Yeah, but double click on the SLN and off you go. All right, so now I'm going to throw caution to the wind and attempt to actually run this. All right, so here I am on Flip. I'm going to SSH rabbit engr.oregonstate.edu. All right, so I'm going to go to where I keep this stuff. And there we are. And so here, well, I've got a bunch of stuff, but I've got the .h's here, and I've got the, well, I called it Monte Carlo.cu. And if I look at the make file, yep, there we go. And I've got some, yeah, use the make file in the notes. I've got some make file isms here that I like to do, but there we go. It's running the compiler. The compiler is called NVCC. It's not G++. Don't run G++. It's NVCC because it needs to extract out that global function and get it downloaded into the GPU and make the connection so you can call it. This is the NVIDIA C compiler. Now, on Linux underneath, it actually does call G++. So the C code will be compiled by G++, but you've got to run the whole thing with NVCC. So if I say make Monte Carlo, tick, 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 there we go, /Monte Carlo, and there we go. This is not the correct probability. I changed the numbers for this video. But here we go. So this is the number of trials. This is the number of threads per block. And this is the mega, mega trials per second. And so if I now run the bash script, there we go. And the reason I want you to develop, debug, test on Rabbit is Rabbit just lets you run this. Like, say, run it. The DGX is a batch submission system, as you'll see. And so it is much more convenient to do all your checking this way. All right, so gosh, we are getting some great performances. Like, look at this one. That's over 1,000 mega trials. That's over 1 billion trials. So you can see that GPU computing really scales well with the size of the data set. You also notice that the size of the number of threads per block makes a difference. 8 is a horrible number to use for that. 16 is a horrible number. 32 is not so great. Yeah, above that, you start to really feed the architecture. All right, there we go. Now, really throwing caution to the wind, let's go over to one of the submit machines. submit.hpc.engr.oregonstate.edu. You have no idea how terrifying it is to run live demos in class, or even on a video. All right, we are on a submit machine. The submit machines don't have GPUs on them either, just like Flip. However, what they have is they are the gateway to the GPUs. First thing we have to do is we have to type in module load Slurm. Slurm. I love that word. Slurm is a package for batch submissions. So you've got to do this because you're going to use some of the batch submission stuff. Okay, I'm going to once again CD to where all this stuff is, and it's the same folder we looked at a moment ago. Okay, however, now I have a bash script called submit.bash, and it's got this. Now, all of these, anything in a bash script that begins with a pound sign, that's a comment. However, the Slurm system will read this anyway. I mean, what it means is bash won't barf on these commands, but Slurm wants to read them. And so this is our account on the DGX for doing this sort of thing. This is our partition when you take your final data. This may take you a little while to wait until you can get in the queue, but once you're inside, once you're running, you have the machine all to yourself. Okay, and this is documented in the DGX notes. Anything printed to standard out will end up in this file. Anything printed to standard error will end up here. I tend to print to standard error, so that's where all mine will be. You can have it email you and let you know how it's doing, like, oh, you started, oh, you've ended, or oh, you failed somehow. And this is the email address to send that to. Don't put Joe Parallel in there. That's not who you are. And be sure to spell it correctly because our systems people, our IT people, get really sick of fielding all those bounced emails when we all spell our name or our own email address wrong. All right, here's the bash script. And I was playing with different versions. 11.7, CUDA 11.7 seems to be especially well tuned for the DGX, and I'm not sure why. Use 11.7, but here we go. It's the nested for loops in bash. To run this, we type sbatch. That's a slurm command. And we want to send this file, submit.bash, over there. And there we go. This is a good number to remember. I like to just double click on it so I can pay. That's a copy in MOBA term, but I'd like to copy it into the clipboard. So if I need to cancel it, like oh no, I've made a mistake and now it's all running crazy. You can do that with scancel and you give it that number. Okay, so here we go. Now, if I do an ls minus lt, and t means what's the most recent thing, oh, look, it's the standard error file. Yeah, okay, not terribly surprising. It's got stuff in it. If I do this again, yeah, it's got even more stuff in it. There's a Linux command called tail that I like. Tail minus F Monte Carlo.err. And what it will do is it will just print out like the most recent things, and then it'll sleep for a few seconds, and then it'll do it again. So there it goes. And so now look at the performances you're getting. 13 billion trials per second, 20 billion trials per second. So yes, you will get better performance. When it's all done, and I went up to 8 million trials, and you can see that, yes, GPUs can handle a lot of data and your mega trials per second gets bigger. So here we're up at almost 40 billion trials per second. Okay, you can also see that a block size of 8 is not so great, 16, not so great, 32, Once you get up about 64, things start to get pretty consistent. Anyway, this is running it. So To get out of tail, you hit Control C, because it doesn't know the job's over. It's just going to sit there and keep looking for updates to that file. But there we go. Your numbers are now in Monte Carlo.err. If it was me and I was going to take this the rest of the way, I would say copy Monte Carlo.err to, I don't know, prod05.csv, because notice it's already in CSV format. Yeah, see, I've done this before. Okay, so that's what I would do. And now you've got a CSV file and you can bring it into Excel. You can do the pivot tables, you can do the graphs, and off you go. But you're going to get pretty interesting graphs out of this. When the top of the graph is up around 40 billion trials per second, those are some good looking curves you're going to have for this project. So welcome to the world of GPU computing. I think this is going to be fascinating. I hope you like it.